Yes. Okay. Very good. Okay. So this is the plan of what I would like to tell you today and tomorrow. Okay. So in the introduction, I will talk about simple things that you may know. Then I will talk about configuration interaction in general. And then I will introduce selected configuration interaction. This is exactly what quantum package is good at doing. And tomorrow I will talk about how to compute multi-determinant wave functions in QMC. Okay, so I will start with the simple things. So just to be sure that we all speak the same language, I will give a few definitions. So we will use atomic orbitals. So atomic orbitals are just simple basis functions like this, where P can be equal to 1 for Slater wave functions or 2 for Gaussians. So it's a polynomial multiplied by an exponential, and so these functions are usually centered at the nuclei, the same positions as the nuclei. And what is important is that it's a non-orthogonal set of one electron functions. And then if you orthogonalize this set of atomic orbitals, you get what we call molecular orbitals, which are linear combinations of atomic orbitals, usually orthogonalized. And then if you try to find the set of molecular orbitals which minimize the energy of a single determinant, you get the Hartree-Fock orbitals. And so if your Hamiltonian is the cone-CHAMP Hamiltonian, then you get the cone-CHAMP orbitals. And then these orbitals, you can do whatever unitary transformation you want. It will not change the energy, and then you can localize them, or you can get different sets of molecular orbitals that are not the optimal ones for single determinant wave functions, such as natural orbitals or whatever. But what is important is that most of the, almost always, these molecular orbitals are an orthonormalized set of atomic orbitals. Okay, and now, so I represented here a single determinant wave function. So the wave function is antisymmetric. So you need to construct an antisymmetric wave function. And so the simplest way is to take all these one electron functions and to make an antisymmetric product of MOs. And then you have an antisymmetric wave function. So I represented here the Slater determinant, where in the columns you have the molecular orbitals, in the rows you have the electrons. And so usually you will have more molecular orbitals than electrons, and so you have to pick the selected set of molecular orbitals that give the lowest possible energy for the wave function. Okay. Okay, so now when we talk about orbitals, so as I said, molecular orbitals are linear combinations of atomic orbitals, and so you can build as many molecular orbitals as atomic orbitals. Okay, it's just a change of representation. So the important point is that the space spanned by the molecular orbitals is the same as the space spanned by atomic orbitals. So this is why when you choose a basis set, then it really determines the calculation you're going to do. Because then once you have chosen your basis set, let's say 631G star, then your MOs will live in the space of 631G star. That's it. So now when you have your Hartree-Fock molecular orbitals, then you can divide them into occupied and orbital and virtual molecular orbitals. So the occupied ones are the ones that are present in the Slater determinant, and the virtual ones are those that are unoccupied, so they are not present in the determinant. It's the complement of the occupied MOs. Okay, so now let's look at the wave function in this way. So the wave function here has n electrons, and so we can choose to put some some labels of spins on the electrons. So here we will say that the up spin electrons are the n up first electrons, and then from n up plus 1 to n, we have the down spin electrons. Okay, it's just a choice. So it's possible to re-express the Slater determinant in such a way that we can divide the Slater determinant. So we can separate it as a product of an upspin determinant and a downspin determinant, where here the upspin electrons are all in orbitals 1, 2, and up, and then the downspin determinants are in orbitals 1, 2, and down. Okay, so if we have the same set of spatial orbitals, then this can be, for example, a restricted open shell Hartree-Fock Slater determinant, and then in that case we use is to understand that you can represent the Slater determinant as a product of two smaller determinants, one with each spin. Okay, so I will represent it like this. The d up and d down, and now if you square your wave function, you should have the probability density in the 3n dimensional space, and so if you square the wave function, then you see that you square the product of up and down spin determinants, and so this is really the d up squared multiplied by d down squared. And this is really the product of an upspin density by a downspin density. So when you look at this this wave function, you see that this wave function is the same as a wave function where you have no electron correlation. Okay, so well you have an independent. Well, the density of the upspin electrons is independent of the downspin electrons. So it's really like if all your up electrons would see just a mean field of the down electrons and the opposite also. So we say that this wave function is uncorrelated. But you have to keep in mind that usually we say there is no electron correlation, but it's not exactly true in the statistical sense, because as your, well, let me go back here. Here, your upspin electrons are not statistically independent together because of the antisymmetry, and the downspin also are not independent with each other. It's just that the upspin don't see the downspin individually. Okay, so so that's it. And so now when we take this wave function, which is a product of these two determinants, we then, when we were doing QMC, we were multiplying it by a Jastrow factor here. And the Jastrow factor contained here terms in which you had electrons of different spins appearing here. So the J here was coupling upspin with downspin electrons. So now when you look at the 3n dimensional density, you see that it's the upspin are no more independent from the downspin, and so the electrons are now correlated. And we define the correlation energy as the difference of between the energy of the wave function with the Hartree-Fock energy. It's just a definition. For correlation energy, we always take Hartree-Fock as the reference. Okay, so I see there is a question in the chat. Let me just open this quickly. Okay, so it's not a question. Okay, so we have talked about orbitals, which are one electron functions. So now we will talk about n electron basis functions. So the wave function is an n electron function. And so if you want to represent it in a basis, you need to take a basis of n electron functions. Okay, so that's what I write here. And of course, if the basis is infinitely large, then you can represent the exact wave function in this basis. by just finding the coefficients here that minimize the energy. And you will converge to the exact wave function. So here, this is the energy of a single determinant wave function, which is higher than one with m electrons. Then here, larger than nd, and here infinite. Okay, so this is the variational principle, which states that the more parameters you have, the lower will be the energy, and you will converge to the exact energy from above. So in this basis of n electron wave n electron functions, there is a natural set of n electron functions that you can take. It's the basis of all possible Slater determinants that you can build with a set of molecular orbitals. So the reason is that these Slater determinants, they are all antisymmetric functions. So then, as you want to build psi, which is antisymmetric, it's a good thing to take a basis of antisymmetric functions, so that you will be only able to build antisymmetric functions combining these determinants together. So you put really a physical constraint in it. So that's a good thing. And the second good thing with these Slater determinants is that they are made of molecular orbitals, and so they are orthogonal within each other. So this makes this has a lot of good aspects to simplify the calculations. So we always talk about excited determinants, etc., but it's you can see it more like Slater determinants are really an orthonormal basis of antisymmetric functions made of n electrons. Okay, so but then of course we can associate a physical picture to determinants, but you can also see it more like a basis. And so the problem with this basis is that it grows very fast, because we have seen that the wave function is the product of upspin and downspin determinants. So here, to build all the possible determinant products of up and down spin, we need to first be able to build all the possible up determinants and all the possible down determinants, and then we would make the outer product of those two sets. So here you see that it grows really factorially. And if you take just this example where you take only 18 electrons in 111 orbitals, you already reach 10 to the 25 determinants. And this is a wave function so large that you cannot store it on a disk. Okay, so such a large space is not something you can handle with a computer. So we will need to make approximations. But the important thing is to see that once you take just when you take the Hartree-Fock wave function and a single other basis function, like another Slater determinant, you see that immediately when you square your wave function, it's no more a product of up and down spin orbitals, just by this expression, and so you introduce electron correlation. So now I will talk. So I've been speaking about Slater determinants. So now I want to introduce what we call configuration state functions. So it's important because it's something which is used in configuration interaction, and also CHAMP works in with configuration state functions. So the exact wave function is an eigenfunction of the spin operator S squared. So the Slater determinants are eigenfunctions of Sz, but they are not of S squared. So when you represent your wave function, when you represent your wave function in a basis of Slater determinants, so if you take, let's say, this one and this one only, you see that you break spin symmetry. Okay, so the total wave function, when you take all the possible determinants, will be an eigenfunction of S squared. But if you just take a subset of Slater determinants, you will probably not be able to have an eigenfunction of S squared. So here, what you need to do is to have in your wave function, in your determinant basis set, you need to have all the spin flips, or the possible spin flips corresponding to occupations of orbitals. So here I took an example where you have 2, 1, 1, 1, 1 electrons. So if you just take this this determinant, this one is not an eigenfunction of S squared, and so to build an eigenfunction of S squared, you need to take this one, this one, this one, this one, this one, this one, or all these 6 determinants, and then you diagonalize the S squared operator in this basis of 6 determinants, and then you get an eigenfunction of S squared with different coefficients A, B, C, D, E, F. And this, the coefficients you obtain here, so you get a small linear combination of these 6 determinants, and you can use these linear combinations as basis functions to express your total wave function. So here, I took in this example the two eigenvectors of S squared that have that correspond to S squared equals 0, which is a singlet. So now, instead of working with 6 basis functions, you can work only with 2, with this one and this one. And in that case, you will obtain a wave function that is an eigenfunction of S squared with eigenvalue 0 for S squared, because it's a property of your basis functions. Okay, so you will be antisymmetric, orthonormal, and eigenfunction of S squared. And so it will be also impossible to represent a triplet in this basis, because the singlet character is encoded in the coefficients of the basis functions. So the CSF basis will also help you target a given spin. And if you want to obtain triplets, then you will work with CSFs that correspond to triplet functions. So because here you select the spin you want, you reduce the number of parameters. This is why you have only 2 functions. And so usually when you work with the CSF basis, so you have the physical property that you're an eigenfunction of S squared, but also you reduce the number of parameters quite a lot. So it's a good thing when you're optimizing large wave functions. And also another important aspect is when you try to do some dissociation curves, because usually when you separate 2 fragments, when the fragments are separated, you have a degeneracy between the different spin states. Like if you separate H2, a dissociation, you have the singlet and triplet that have the same energy, and so if you make a dissociation curve and you don't impose that you have an eigenfunction of S squared, then you will start to have some mixing between the spin states, a dissociation, and you have some problems of convergence and non-regular curves, etc. Okay, so now configuration interaction. So in configuration interaction, your wave function is a linear combination of Slater determinants or CSF, because there's a one-to-one correspondence between the two. And you minimize the energy by diagonalizing the Hamiltonian in the basis of the Slater determinants or of the CSF. So it's really a linear parametrization of your wave function, and you minimize the energy. So the different CI methods, they it's always the same idea to diagonalize the Hamiltonian, but what is different is how you build this Hamiltonian. Okay, so it's always the same Hamiltonian, but in a different choice of determinants or CSF. So the simplest of all the CI methods is the full configuration interaction, full CI, where you take all the possible Slater determinants. So it's really it includes everything. It's really the exact solution in the predefined basis set of all possible Slater determinants. And then if you take the full CI space and you remove some determinants, then you go back in, you go into all the other definitions of CI methods. So let's say if you remove everything except all the single and double excitations with respect to the Hartree-Fock determinant, you get the CISD. So now if you take the full CI, but and you remove everything that where you have excitations out of an active space, then you get the complete active space. So it's very important to understand that complete active space or CISD or CISDT, they are all subsets, they're all different subsets of full CI. And really the idea of these methods is really to approximate the full CI, because this is really what you want to compute. But the problem, as I said, is that the scaling is it grows too fast. And so you can never really make a full CI calculation. So this is just a way to reduce the computational cost and to make it fit in the computer by trying to put the physical ingredients you want. So the physical ingredients, well, it's just electron correlation, but we usually separate the correlation into two different types of correlation. So we say we have dynamic and static correlation. So dynamic correlation corresponds to really short-range effects due to the Coulomb Hall. So the physical picture is really when you have two electrons approaching each other. What is the response of the wave function to this? So dynamic correlation, you will not change that much the Hartree-Fock picture, okay? Because the Hartree-Fock, you will have the Hartree-Fock density, and this will be just very local, small corrections for dynamic correlation. But static correlation is very different. It's more near degeneracies. So it will be more like when you have two or more states with very, very close energies, and they are all making interference with each other. Okay, and so when you have important static correlations, the Hartree-Fock picture is usually qualitatively incorrect. And so you need to go to multi-configuration methods. So here I took just a simple example. So the CH4 molecule. So this one is very well described by Hartree-Fock determinant. And when you introduce electron correlation, you mostly include dynamic correlation, and you see here the difference between the correlation energy between the full CI and the Hartree-Fock with 38 million determinants. You see that here you gain, I would say, 0.12 atomic units. So it's not that much with 38 million determinants. But now if you take dissociated H2, with only two determinants, you see that the Hartree-Fock energy is minus 0.5. And when you take the CI with two determinants, you get to 0.94. So here, just with two determinants, you get 0.4 atomic units of correlation energy. And you see here that the energies of the orbitals are the same because you really have degenerate orbitals. Okay, so you really need to include those two states to describe properly your system. And as these two Slater determinants have an important weight in the wave function, you really see that the Hartree-Fock density is really a bad representation of the wave function. Okay, so now I will speak a little bit about the Jastrow factor. So the Jastrow factor here that we multiply by the determinantal component of the wave function. So this Jastrow factor is really well adapted to describe dynamic correlation, because I said it's local short-range effects for the Coulomb hole, and this is really well described by the Jastrow factor. And static correlation, which corresponds to quasi-degenerate states, this is really well described by linear combination of determinants. So an optimal representation is to take both ways to represent correlation together in the same wave function. So to use this part here to represent the static correlation, and the Jastrow factor to represent the dynamic correlation. And sometimes you have some feedback of dynamic correlation on the static correlation. So you have a coupling between the two. And in that case, after introducing the dynamic correlation, you will need to re-optimize the coefficients of the determinant expansion in the presence of the Jastrow factor to have a better description of your system and a coupling between the static and dynamic correlations. So another important thing you need to consider when you build your wave functions is size consistency. So here I will talk about strict separability. So what is this? It's when you have two systems, where you have a system AB, and you split it in two. So you stretch them so far that at the end they don't interact anymore. And what you would like is that the method you use to compute AB is of well, the quality to describe AB is similar to the quality to describe A and B. And so to check this, once you split your system, if you use the same method to compute AB at a very large distance, and then you compute the energy of A and the energy of B alone, you should see that the energy of A and the energy of B should add up to the energy of AB. So this is a property that you want, because it will mean that that when you make, let's say, a dissociation curve, or when you make some reactions or things like that, your energies will be consistent at every point of the potential energy surface. So you see that if your molecular orbitals are localized on fragments A and fragments B, then your so you see that you can really build your total wave function as the product of the wave function on A with the wave function on B. Okay, and this is a property that you have at the full CI level. So when you make a full CI calculation, you obtain size consistent wave functions. You can always you can check that you really have the full CI wave function of AB stretched at infinity is really the tensor product of the full CI of A multiplied by the full CI of B. But this is not generally the case when you do configuration interaction. Usually, CI wave functions are not size consistent. So we can take here the example of CI with single and double substitutions. So, if you want to check it, you can see that you can take the system AB stretched very far, and you try to build so you localize your orbitals on A and B, and you make the CI, you build the CISD space. So what you will see here is that so if you take system A, you will apply all the single and double excitations on the Hartree-Fock determinant of A, okay? And you do the same for B. And now when you try to combine A and B together, you see that you will need to do all the singles and doubles on A and also all the singles and doubles on B. And so you will reach up to quadruple excitations, okay? Because you will have some double on A, double on B, and that's a quadruple on AB. So if you have AB together and you just do a CISD, you will not build in your space all these quadruple excitations and the triples ones. And so you will not have the same description at the CISD level for AB. You will not have the same description as for A alone at the CISD level and B alone at the CISD level. And another way to see it is that when you do CISD on AB, if you have a double excitation on A, it implies that you have the Hartree-Fock on B. Okay, and if you make a double excitation on B, it implies that you have a Hartree-Fock on A. So you introduce here some coupling, some spurious correlations between A and B, which is not physical, and you will have an energy which will be higher than the energies of the independent systems. So in the configuration interaction wave functions, so usually you're not size consistent, except in a few cases. So in the cases where you make a full CI calculation in a subspace of orbitals. So the simplest one is Hartree-Fock. So Hartree-Fock is size consistent, full CI is size consistent, and CAS-SCF is also, or even CAS-CI, is size consistent because it's a full CI in a space, in a restricted space of orbitals. Okay, so let's move on to configuration interaction. So how do we make a configuration interaction? So as I said, we define an orthonormal basis of an electron functions, so the Slater determinants or the SCFs. And then we will express the wave function in this basis. So when we take the projection of the wave function on these determinants, as it's an orthonormal basis, you will immediately get the CI coefficients here. So the wave function will be normalized, and that's the expression of the energy. And the optimal coefficients are obtained when psi is an eigenfunction of H. So H will be the operator projected in the basis of determinants that we have chosen, and E will be the eigenvalue. So to obtain this energy, we'll need to diagonalize the Hamiltonian in this basis of Slater determinants or CSFs. So we will have to write these matrix elements IHJ. And so this diagonalization will be possible. So we will be able to do a complete diagonalization for small matrices like 10,000 or maybe even 100,000, but not much more. And when the number of determinants is going to get larger and larger and larger, it will not be possible to diagonalize exactly the Hamiltonian, and we will then use other methods than exact diagonalization. So we'll do iterative diagonalizations with, for example, Davidson's algorithm to extract the lowest eigenvalues and eigenvectors. So to do that, it's important to keep in mind that it will be a power method. Okay, so we will apply the Hamiltonian to a trial wave function. So we'll do H applied to psi, and we will project the result in the basis of Slater determinants. That will be this vector W. And then we apply H on W. It will give you a W prime, and then you apply H iteratively like this. Always you apply H on the same vector, and then you will converge to the eigenstate of H. So the bottleneck of Davidson's algorithm will be the application of H to a vector. So it will be a matrix vector product in a large space. In a matrix vector product of dimension ND, where ND is the number of Slater determinants or CSF. So yes, you have seen here that when you diagonalize this matrix, you need well, at the end you're just doing linear algebra matrix vector product, and the matrix elements Hij here. This is how you obtain them. So I've said before that your molecular orbitals are orthonormal. And so a consequence of this is that the Slater determinants are also orthonormal together. And a consequence of having everything orthonormal like this is that you can calculate very easily the matrix elements of H in the basis of Slater determinants. So these are what we call SlaterCondom rules. So this is really a consequence of having an orthonormal set of MOs. If you don't, then everything breaks down, and you cannot calculate easily these terms. So with SlaterCondom rules, you see that the diagonal terms are expressed like this. Singly excited determinants have also a simple formula. Doubly excited determinants also, and then if you have two determinants which differ by more than two molecular orbitals, then the Hij is 0. Okay, so basically when you compare two determinants, if they differ by more than two MOs, it's 0. If they differ by exactly two MOs, you just have to pick one integral. And if they differ by one MO, you need to make a sum of integrals, and the diagonal terms are with an expression similar to the Hartree-Fock one. So it's really simple. Once you have the integrals in the MO basis, then you have everything you need to build the matrix Hij. So I'll try to continue a little bit. Yes, about the computational aspects of configuration interaction. So I've shown here that the only thing you need to do a CI calculation is to have integrals, and there are not that much integrals. You see, there are n to the power 4, where n is the number of different molecular orbitals. Because here you have PQRS. And so you have n to the 4 different combinations of these. But the number of Slater determinants, I've shown before that it grows exponentially. So it makes more sense to consider only the non-zero integrals. And once you have chosen an integral, you just need to see where is going to contribute in the matrix. Okay, so let's do it. Let's go back to here. So the traditional, the easy way to build the Hij matrix would be really to iterate over the determinants over row and columns, and then you take your determinant I and your determinant J, you compare them, you use the SlaterCondom rules. Where are they? Sorry, yes, you take the SlaterCondom rules, you check by how much they differ, And then you put your integrals or your sums of integrals inside the matrix Hij. But that is terribly inefficient, because most of the time, when you will compare I and j, they will differ by more than 2 MOs, and you will do a comparison to check that Hij is 0. Okay, so it's going to be very expensive. A much smarter way to do this is to iterate over the integrals, PQRS, and then once you have a PQRS in your hand, you try to find the couple Ij where it contributes, or also well in the I would say in these elements, in those ones and those, because you see here that an integral can appear here in Ij differing by 2 MOs, but it can also appear in an element here, or probably here if it has the form Ij. Okay, so iterating over the integral is always much more efficient, because you never have to do anything where it's 0. So most of the codes have been developed using what we call integral-driven algorithms. And but the thing is that when your code is designed to loop over integrals, it also changes the way you think the methods. And so the methods are also developed in such a way that they can be easily implemented with integral-driven algorithms. And this is the case for all the CISD, CISDT, couple cluster, and also all the CAS SCF methods are very well adapted to integral-driven algorithms. Okay, so determinant-driven algorithms have been known to be much more costly than integral-driven algorithms. But the thing is that so CPC, what I'm going to introduce probably after the break, you will see that we will use determinant-driven algorithms, and so really the code is completely different from the usual codes like Molcas, Molpro, games, because the engine to make the CI calculation has to be completely different, and all the code has to be thought in a different way, because you're no more iterating over integrals. You're really comparing determinants together with SlaterCondom rules. So, but I will get back to this aspect. So I've been speaking about diagonalizing the Hamiltonian. So you can of course get the ground state, but you can also get excited states. So excited states will be the states that are not the states of the lowest energy, and there are 2 different categories of excited states. Okay, so the first one will be excited states with the same symmetry as the ground state. So these are obtained as different eigenvectors of H, and they are usually expanded on the same set of determinants. Okay, but you could also have states of different symmetries. For example, you could have a ground state of symmetry A1 and an excited state of symmetry B2. And in that case, A1 and B2 are expanded on different determinants, and they are you could have the lowest state of A1 symmetry, and also the lowest state of B1 symmetry, and there is no real problem in well, the lowest within each symmetry is usually easy to obtain, because it's really it's the lowest state of a submatrix of the Hamiltonian. Okay, because if you have some symmetries in your Hamiltonian, then the Hamiltonian is block diagonal within the symmetries, and then you can really block diagonalize your Hamiltonian, and you can get the lowest of each symmetry quite easily. it's harder to get an excited state of the same symmetry as the ground state, because if you have a bad description of the lowest state, you will also describe badly the excited states because they are orthogonal to each other. Okay, so if you have a badly described ground state and you take an excited state of the same symmetry, it will your excited state will be orthogonal to something which is badly described, and so you might get also something wrong. So it's important to keep in mind that when you have excited states of the same symmetry, you need to have all the states below that are well described so that you get something which is relevant. So now let me check. Yes. So to summarize, so all the configuration interaction methods are approximations of the full CI, because this is really what we all want to get. So when you compare numbers with approximate methods, usually it's better to compare them to the full CI in the same basis than to the experimental results, okay? Because the CI is an approximation of the full CI, and the full CI is itself an approximation of the real number. But when we make a truncated CI calculation or a CISD or couple cluster or whatever, we're really trying to get the full CI number more than the exact results, okay? There are sometimes you could get the exact results because you have some error compensations, but when you really want to check the accuracy of a method, you should compare it to full CI. So all these different CI methods, basically you just diagonalize the Hamiltonian in the basis of Slater determinants. So the only difference between all these CI methods is the choice of the Slater determinant basis. So there are two main directions. So the first one is increasing the excitation level from Hartree-Fock. So singles, doubles, triples, etc. So you increase in this direction. So this will introduce dynamic correlation mostly. Or another way to increase the CI space is to take Hartree-Fock and include one or more orbital, two orbitals, three orbitals, etc. So you increase an active space in the middle, but you do always the full CI in this active space. So doing this, you will be size consistent, but the size of the CI will grow exponentially also because you will do always a full CI in a small space of orbitals. And so going in this direction, we introduce static correlation as opposed to this one. So I've told you that to combine static and dynamic correlation, you could use CI expansion and a just flow factor. You can also do it by combining these two approaches. So taking a small active space and then doing all singles, doubles, and triples, etc., on top of a cast wave function. And so this is what we call a multi-reference CI. So you have an active space, and then you do all the singles and doubles on top of this wave function. And it's a way to introduce both static and dynamic correlation. But you see that if you do it, you have the problem that you have with CISD, is that you will not be size consistent. But the size consistence error will be small, but nevertheless, it will introduce a small error like this. And another way to introduce dynamic correlation on top of static correlation is to use perturbation theory. So if you do it on the Hartree-Fock, then you have MP2, but then you can do also CAS-PT2, which is quite a popular method to have both effects at the same time. And perturbation theory is cheaper than CI, so that's why CAS-PT2 is quite popular. So yeah, I think it's a good time to take a break. So we talk about selected configuration interaction after the break.
So, Anthony, there is a question about, yes, you kind of answered before, or maybe you can repeat it, is what kind of contribution to the correlations, I guess, static and dynamics, is more dominating?
So when you have, so I will go back to this slide.
Yeah.
So I had an example with CH4 and H2. Let me go back to it.
Yeah.
So usually static correlation, if you miss it, you make a very, very large error in total energy. Okay. So it depends. If the static correlation is important, if you miss it, you're completely wrong. But if the static correlation is not that important, then you might not see too much there. You should consider that you always have static and dynamic correlations, always, but with different weights. So in CH4, most of the correlation comes from the dynamic, and so you see here with 38 million determinants, you have 0.2 atomic units, and here in H2 with 2 determinants, you have 0.4. So you see that static correlation can be really, really, really important. So I will now continue, and we'll talk about selected configuration interaction. So we have seen that the full CI is the exact solution of the Schrödinger equation in a complete basis set of Slater determinants. And so we have seen that the determinant basis is derived from the one electron basis set. So the only approximation that you're doing with full CI is the one electron basis set incompleteness. And we have seen that it's intractable, so we have a factorial scaling. And all the post-Hartree-Fock methods are approximations of full CI within the same basis set. So in my previous answer to DMRG, I just want to make to complement the answer, because in fact what I said about DMRG CI, it's the same for all the approximate methods. The only method that can be trusted is full CI, because you know that you make the exact calculation within a basis set. But then once you remove some determinants of the full CI space, you remove the possibility to describe some effects. So if you just do a small CAS SCF, then it will be impossible for you to describe dynamic correlation. And if it's important for the system you study, then CAS SCF cannot be trusted for this particular system. In the same way, if you have a system that really requires important description of static correlation, if you use CISD or CCSD, it will not work. So all the methods that are approximations of the full CI, they can be trusted only if in your determinant space you have what is necessary to describe properly the system. Okay. So now I want to show you. So I'm going to talk about full CI. So the largest CAS SCF that has been done recently. So maybe there was one more recently, but I'm not aware of it. So in 2017, there is this group. They have been able to do a CAS SCF, a very large CAS SCF with 22 electrons in 22 orbitals, which was the world record. And they were even able to do a single CI iteration of 24 electrons in 24 orbitals. Okay, so if you count how many determinants you have in this space, it's 914 billion determinants. So it's really an enormous CI calculation. It's the largest conventional CI calculation attempted up to date in 2017. So I'm not aware of a larger calculation than that. So it's important to keep in mind that if you want to do a CAS SCF with more than 22 electrons in 22 orbitals, it's going to be very, very, very hard. But so as I said before, the good news with the full CI Hamiltonian is that it's very sparse. So in each row of the Hamiltonian, you have seen with Slater rules, you have non-zero elements only when J differs from I by less than 3 molecular orbitals. Okay, so this means that the only non-zero elements in one row are the diagonal element and the single and double excitations, and this corresponds to n squared occupied multiplied by n squared virtual elements, non-zero elements per row. So you have of order n, I would say order n4 elements that are non-zero in each row. So in this space that grows factorially, you see that the matrix has mostly zeros and just a few elements that are non-zeros. So as the Hamiltonian is symmetric, everything which applies to rows applies to columns, so it's the same. And we've seen that in Davidson algorithm, we compute IH psi. As I said, it's just a sparse matrix vector multiplication. And the scaling of this sparse matrix vector multiplication scales as the number of non-zero elements in each row multiplied by the number of determinants in the space. And as this thing is usually larger than this, you see that with Davidson's algorithm, basically at each Davidson iteration, the cost is, well, it could be brought down to something proportional to the number of determinants. So in full CI, there has been a breakthrough starting from 2007 to between 2007 and 2012. So the first one was when DMRG was applied to large CAS wave functions by Garnet Chan, and then there was the group of Ali Alavi where they developed the full CI QMC approach. So full CI QMC is a stochastic solution of the full CI equations. So full CI QMC is not the same as what Claudia has presented in QMC. It's really you try to solve the full CI but using stochastic algorithms. And so before 2007, it was really full CI was something that was impossible to reach except for very tiny model systems. But then full CI QMC was able to give full CI energies of the first row diatomics with quintuple zeta basis sets. So it was really a very important gap that has been filled by this algorithm. And then selected configuration interaction came back because with selected configuration interaction, the scaling is still factorial. So it's so this answers one of the questions of the chat. But the prefactor is really killed. Okay, so so it makes calculations possible on larger systems than complete full CI, but still you will never be able to make a calculation on a protein with a selected full CI. And so with selected configuration interactions, we can use much larger active spaces than doing complete full CI. So I've shown before that you had the full CI of so this one 22 electrons in 22 orbitals when you do everything exactly. But now in open Molcas, it's possible to use the full CI QMC solver to do the CAS part of the CAS SCF, and here it allows to use much larger active spaces than when you do the calculation exactly. And so in Molcas you can also use the DMRG algorithm, and there is this paper of the group of Sandeep Sharma, where they have been using selected configuration interaction to as a solver for the CAS, also using HCI the HCI selected configuration algorithm, and they were able to do 44 electrons in 44 orbitals with only 412 seconds on a single node with 28 cores. So if you compare this calculation, so there were twice as much electrons, twice as much orbitals, and it was running only on 28 cores. And this has to be compared with this calculation, where if you look at this paper, they were really using massively parallel CI calculations on a huge number of resources. I think it was around 10,000 cores, if I remember. So it was really a very, very large calculation. So you see here that just changing the algorithm and accepting to make a little error, then you can gain an enormous amount of computational time. And this calculation will not be feasible with computers even in 20 years in an exact way. I mean, it's impossible to store the full CI wave function of 40 electrons in 40 orbitals. So selected configuration is really an answer to do some very large active spaces. So what is selected configuration interaction? So it's just a way to select determinants on the fly. So in all the presentation of this morning, so I was talking about the CI methods, the CISD, CISDTQ, etc., and CAS-SCF. But in these particular methods, you were selecting the determinants before doing the calculation. So the space of determinants was predefined. So with selected configuration interaction, it's different. So you predefine a space. So usually it will be the full CI space, and then you select determinants on the fly. And you try to find what will be the determinants that will lower the most the energy. And you select these determinants along the calculation. So there are different ways to select these determinants. So you can select them with perturbation theory. So this will be SIPC. So SIPC, it's a very old idea. So it's 1973. It was quite popular in these times. Because the computers were not like they are today, and so there was really no even making a CISD calculation was something very very expensive at that time. So it was interesting to select determinants so that you could reuse as much as possible the wave function and have something very compact. But then these methods have been forgotten a little bit, because then with all the technology developed with these integral-driven algorithms and CAS-SCF, etc., then nobody has been using SIPC anymore for a long time. And then when the full CI QMC arrived, we in the lab with Michel Caffarel and Emmanuel Giner, we rediscovered SIPC, and when we started to implement it on modern computers, we saw that it was really an interesting alternative to get some full CI energies, and so it came back at that time. And so a few years later, there was the Cyrus Omrigar, who developed this SHCI, where it's a different way to select the determinants. So we select them by perturbation theory, and in SHCI, the selection is less accurate, but it's less costly, because here you need to do a perturbation theory calculation to estimate if you're going to introduce or not a determinant, and in SHCI, it's just the magnitude of the matrix element of H. So it can be done with integral-driven algorithms. So it can be, so the selection can be super fast. And so here, selected CI, it's not really a method. It's just a way to. So it's an algorithm to solve a CI problem. So you can predefine a target space. So it can be a full CI, it can be a large CAS, it can be an MR-CISD. And then once you have selected this space, once you have chosen the space at the beginning, then you can run your CI calculation using selected configuration interaction. So if suppose your CISD is too large, then you can do, if you want, you can try to approximate the CISD with selected configuration interaction in this CISD space. So that's why I prefer not to say that selected CI or CFC. For me, it's not really a method. It's an algorithm to solve the CI problem in a larger space. So that's why I would say that selected CI is has a factorial scaling as full CI, because if you let selected CI run with an infinite amount of time, it will converge to the full CI with an exponential scaling. But if you run selected configuration interaction, if you run a CFC algorithm on CISD, it will not be exponential. It will be asymptotically the cost of CISD. And also the nice thing is that you select some determinants, so you don't select the whole space, your whole target space, and what is missing, you can use perturbation theory to estimate the missing part. So here is the CFC algorithm, so that you understand how it works. So you start with a determinant space. So usually we just take one determinant in this space, the Hartree-Fock determinant, and we expand the wave function in this space of determinants. So in this starting case, it will be so the starting wave function will be the Hartree-Fock determinant. And then on this wave function, we apply all the single and double excitations that we can. And for each one of these single and double excitations, we estimate this quantity EI. And this is the contribution of determinant I to the perturbation theory correction. Okay, so if you compute the Epstein-Nesbett perturbation theory on Hartree-Fock, you will make the sum over all the determinants I of these quantities. So this really measures how much energy you would gain by introducing I into the determinant space. So you compute EI for all possible singles and doubles, and then if this contribution is above a threshold, then you select the determinant. You say this one will bring a lot of energy. I will select it for inclusion into the determinant space for the next iteration. And as you compute all these EI, if you make the sum of all these contributions, then you get the PT2 correction to the current energy. Okay, so here we will estimate the full CI energy as at the first iteration as the Hartree-Fock energy plus the sum of all these contributions. Okay, so now we have selected these determinants, and we can create a new determinant space, which is the determinant space of the previous iteration, so D0, and we include all the selected determinants. So now we have a space, let's say, of if I had selected 10 determinants here, I would have now a space of 11 determinants, the Hartree-Fock plus the 10 selected determinants. And now I can build my Hamiltonian in this space of 10 determinants. I can diagonalize it. And then I get this new wave function psi n plus 1. So I adapt now this epsilon n. I reduce it a little bit. And then I go back to this, to step 1, where now I apply all the singles and doubles to the wave function that is now made of 11 determinants. I calculate the contributions of all the external determinants, and I select the good ones, and then I iterate. So the wave function grows with time. And if I let the calculation run without never stopping, I will reach a point where all the external determinants have been selected. So there is nothing in the external space. The PT2 here will be a sum of nothing, so it will be 0. And all the determinants will be included in the space. I will diagonalize, and I will then obtain the full CI energy. So this is what you can see on this graph. So here you have the number of determinants of the space, of the variational space, number of determinants that have been selected. and here you have the energy. So this is this little molecule. So the green curve here is the variational energy of the ground state, and this one is the variational energy of the excited state, or the first excited state. And here, this curve here is for the ground state, this one is for the excited state, and so this is the variational energy plus the PT2 correction. Okay, and so what you see is that here you have the Hartree-Fock energy. Well, it's a little bit before. So you have the Hartree-Fock energy, and then at the first iteration, you get here, and you see that every time you grow the space, you rediagonalize, and the variational energy it always goes down at every iteration, and ultimately it will converge to the full CI energy. And now, if you take E plus the PT2 correction, well, you see that you overshoot. Well, so this you cannot really predict if you're going to overshoot or undershoot. But what is interesting is that the PT2 correction goes to 0 when you converge to the full CI. So you see that these two curves are going to they are going to cross at the once you reach the full CI, because the PT2 correction is going to be 0. And so you have this for the ground state and also for the excited state. And so what you see, you will always have this kind of profile, and it's important to keep in mind that you can use really this selection algorithm for any kind of CI calculation you want to do. It's not only for full CI. And okay, so now how do we estimate the full CI energy? So these two curves correspond, this one to the ground state and this one to the excited state. So what is really this curve? So basically it's the extrapolation of the variational energy, the extrapolation of this one as a function of the PT2 correction. Okay, so here you have the PT2 correction is negative. So you see here this curve here. So this is this point here is minus 149.6. So you see it will be this this point here, and then it will go down until it reaches minus 150, which is somewhere here. So you see it's really these energies, but as a function of the distance to the full CI. And so what we know is that when the full CI is reached, the PT2 correction is 0, and so we can extrapolate these curves to PT2 equal to 0, and then we can get an estimate of the full CI energy. And we can do it for the ground state and for the excited states. Okay, so let me see. Okay, so now the big difficulty with this approach is that there is no so on what I've shown here, you see that these curves, the ground state and the excited state, they are mostly parallel. Okay, and when the curves are parallel, if you want to calculate an excitation energy, so if the two curves are always parallel, it means that you will have that the energy difference that you have at the full CI level will be kept constant along with the whole curve. And this is really what you want, because you know that you will never be able to reach the full CI for such a system. And so you want to reach the point where the two curves are parallel, such that you have a very good estimate of the excitation energy, even if you have selected just a small amount of determinants. But there is really no guarantee at the beginning that it's going to behave like that. Suppose you take Hartree-Fock orbitals for the ground state. So the Hartree-Fock orbitals for the ground state will be very poor orbitals for the excited state. And in that case, your excited state will be too high with the same number of determinants. And you will not have curves that will be parallel like this. Okay, so you will have an excitation energy that will be overestimated for small numbers of determinants, and then you will see that along the selection, the excitation energy is going to be smaller and smaller, and then it's going to reach its value of full CI. On the opposite, if you take now orbitals that are optimized for the excited state, the description of the ground state will be bad for a small number of determinants, and then it will be too high, and so you will underestimate your excitation energy. And then the excitation energy will grow along with the selection until you reach the full CI. So all the problem, if you want to get some accurate excitation energies, you need to have some comparable quality between all the states along the curve. And so, so the idea here is to use a state average orbitals such that your orbitals are equally bad for all the states, and in such a way that the curves will all have the same rate of convergence to the full CI. So this is what I try to represent here. So the full CI energy will be always estimated as the energy plus the PT2 correction. Okay, so so basically the error you make on the full CI will be proportional to the magnitude of the PT2. Okay, and so now if you look at two states like this, if they have a different rate of convergence to the full CI, you will have different values of alpha here. But if you can make this alpha the same, so this means that your two curves here will be mostly parallel, because the error you make here will be comparable to the error you make here. When you make an energy difference, the alphas will cancel out each other, and the difference, the energy difference at the full CI level will be the same, more or less, as the energy difference that you have at the variational level with the truncated wave function. So all the game is to make this alpha here equal. And so what is the this alpha here? Basically, it's the slope of the extrapolation curve. Okay, so if the slope of the extrapolation, if these two curves are parallel, then you see that for the same value of the PT2, if you have a constant value of the PT2, then you basically get the full CI energy difference. So what we try to do when we make this kind of curves, so first thing, we start with state average orbitals such that the slopes tend to be equal. And then when we do the selection with SCFs, we try to adjust the weights on the ground state and the excited state and select determinants such that the PT2 correction on the two states is the same. Okay, so let's say if at some point we calculate that the correction, the PT2 correction of the ground state is larger than the PT2 correction of the excited state, we are going to then put some more weight on the ground state, in such that we are going to introduce more determinants for the ground state, such that at the next iteration, the two PT2 corrections will tend to be equal. And then if the PT2 corrections are equal and the slopes are parallel, then we get a very good estimation of the excitation energy. So basically, that's how we compute excited states with SCFs. So I will stop here with the lecture. So tomorrow we'll talk about this using SCFs to do multi-determinant QMC. Let's come back to the hands-on sessions. Okay, so so before we do anything, so now I have introduced a little bit SCFs this morning. So I propose that we look together at the output of SCFs calculation, so similar to what you should have done last week. I'm just going to show you how the output is related to what I've shown this morning. So that's the output of the H2O molecule doing the CFC calculation in the full CI space. So here, well, at the beginning you have the nuclear coordinates. Then we compute all the integrals in the atomic orbital basis. Then we do the AO to MO integrals transformation, so that we have all the molecular orbitals in the basis of MOs, and these are the integrals we're going to use to construct the Hamiltonian. So here I've been using the Hartree-Fock orbitals. So I start with one determinant, the Hartree-Fock determinant, and so I go down. So there are lots of prints. So yes, so here we have the so we diagonalize a 1-by-1 matrix. So we are doing the exact diagonalization here because it's a very simple one, and we get here the energy. So this is the Hartree-Fock energy of the wave function. And now we are going to generate all the singles and all the singles and doubles. Yes. Okay, so sorry. Here we have the summary for one determinant, and we have computed the PT2 contribution, which was the sum of all the contributions of the external determinants. So the PT2 contribution is 0.258. So the estimated full CI energy with one determinant is 76.285. And this RPT2 is the renormalized PT2 I was speaking about, the one which has a more linear extrapolation curve. Okay. So you see they give different values here. And so, okay, so this basically is the same as what we've seen above. And yes, so now we have selected some determinants, and we are going to diagonalize it again. So you see here, we are at 76.052. So we are a bit lower. So yeah, so we have 9 determinants. We are here, and so the PT2 you see is smaller now, is 0.21. It was 0.25 above, and so now if I continue like this, you see that here this variation energy is decreasing. The PT2 is getting smaller and smaller, and if I go on like this, and I go on, you see it's always the variation energy is decreasing, and the PT2 is getting smaller and smaller and smaller. Okay, so you see it goes down to this value for 180,000 determinants. So so between these summaries, you should have some tables like that. So these correspond to the calculation of the PT2. The PT2 contribution is here, and here you see it's displayed like this because we use a stochastic algorithm to compute the PT2. So that's why you have an error bar on the PT2, because making the exact calculation would be too costly. So we just use a stochastic algorithm that makes it quite fast. And while during this stochastic calculation of the PT2, this is where we generate the external determinants and select them. So there is also a stochastic selection of the determinants. Okay, so that's it. So yes, and after the summaries, so let me go back at the top. Okay, after the summary here, you should have extrapolated energies. And so here you have the estimated full CI energy. So this is for one determinant. So now if I advance, you see now I have two values. So this is the 2-point extrapolation, and this is the 3-point extrapolation. So now if I go to the next one, I have the 2.34 point. Okay, because every time I add a new value, and here the extrapolation gets more and more accurate. So this is the magnitude of the PT2 beyond which you start to do the extrapolation. So what you see here is that the value of the PT2 at the current point is minus 0.14. The point before was 0.16. The point again before was 0.18, etc. Okay, and so if you continue like this, you see that, well, here we're at 175 determinants. What we see is that the extrapolation with 2, 3, 4, 5, 6 points, they all give different answers. But what we know is that at least we can, we know that the 76.23 is a reasonable answer. We're only not sure about the last digit here. And then we continue. And at some point, we will see, like here, that the 3 first digits have converged, and so we can be pretty sure that that we're close to the full CIA value here. So also, as a rule of thumb, you can estimate that the error you will make on the extrapolation will be more or less like 10% of the PT2. Okay, it's just to get an idea. It's an empirical rule. So here, when we get to PT2, which is 10 to the minus 3, here we have really we are below the millihartree accuracy on the extrapolated energy. And you see that the PT2 really goes to 0 when you push far enough, and you see that everything stabilizes well, and you converge to the full CI energy. Okay, so that was just to understand the output. And when you make multi-state calculations, you will have a PT2 for the ground state and a PT2 for the excited state, and then you will have extrapolated energies for the 2 states. Okay, so now excited state calculations. So okay, so what we're going to do here, we are not going to generate the SCF with quantum package. We're going to take a TREX-IO file containing a wave function, which is a SCF orbitals obtained from games. So the reason is that we are going at the end to do the optimization of the states with a CHAMP. And CHAMP can take advantage of symmetry to reduce the number of parameters. And quantum package doesn't work with symmetry. So here we will have the information of the symmetry of the orbitals inside the TREX-IO file. So that's why we will take a wave function computed with games. So we will. So this is how you can get the TREX-IO file. So this formaldehyde. And you will use this command qp import TREX-IO to import the data from the TREX-IO file and transform it into an easy FIO database. Then you will tell quantum package you want to make a 2-state calculation. Here you can set where you want to stop the CPC calculation. So after, let's say, 2000 determinants, and then you will run the calculation. So you will really run with selected determinants for the 2 states at the same time. So the expected energy, so we expect to get 4 electron volts, and we will get 8. So I'll let you probably do this right now, and then we can come back to this point, and I will explain you why you get 8 instead of 4 and how to do things properly to get 4 EV. So now I let you do it. So let's look together at the output that you should have obtained. So I'll share my screen. Share. Oh. So you should have an output like this. So where you have here the extrapolated energy of the ground state, here the extrapolated energy of the excited state, and here you have also the energy difference between the ground and the excited state. So you see that the energy is around 8 electron volts. Okay, so I told you that you should have obtained 4. So this means that we didn't catch the correct excited state. So the reason is related to what I said this morning about excited states. So the excited state we would like to catch is not in the same symmetry as the ground state. And so when we start from the Hartree-Fock determinant, we make all the single and double excitations on top of the Hartree-Fock determinant, and we select determinants like that. But if we have another determinant that is not in the same symmetry as the ground state, by symmetry, the matrix elements will be 0. And so we will not be able to introduce inside the variational space determinants which are not of the of different symmetries. Okay, so just by the SCFs algorithm starting from Hartree-Fock, we will be only able to select determinants that would generate excited states of the same symmetry as the ground state. So so we need a way to introduce inside the space determinants with different symmetries. So so there is a very stupid way, which consists in performing a CIS calculation. So a CIS is CI with all singles. So you take the Hartree-Fock determinants and you make all the possible single excitations from the Hartree-Fock determinant. And by doing that, you are sure that you will produce at least one determinant of each symmetry. Okay, so when you do the CIS, you put inside your space all these determinants. So this is what I propose to do here, is to perform a CIS calculation. So then you run the CIS, you diagonalize your Hamiltonian in the CIS space. So you will have a vector in the CIS space, and then you tell quantum package to, instead of starting from 0, you say, I want you to continue the calculation, and so I want you to read the wave function that is inside the EasyFIO and to start from this to perform the SCFs algorithm. So the SCFs will continue after the well, using as a trial wave function the CIS. And so when you will diagonalize the Hamiltonian, then you will be able to describe states that are of different symmetries, and then the state you want will appear in the diagonalization of H. And so the whole idea here is also to make a QMC calculation after. So we want to make a wave function with a very small number of determinants, because for QMC it's going to be easier to optimize if we have a tiny number of determinants. So we want the selection of SCFs to be made slower. So by default, what quantum package is going to do, quantum package is going to try to double the size of the wave function at every iteration. So if you start with one determinant, it's trying to make 2, then 4, then 8, then 16, etc. And every time you're going to double the wave function, you're also going to add all the determinants in such a way that you will be able to make an eigenfunction of S squared. So let me go back to what I said at the beginning. Yes. So when with quantum package, you're going to add this determinant here. If this one is selected, then in a deterministic way, all the other ones are going to be also included, such that when you diagonalize, you will be able to have an eigenfunction of S squared. So this is why the wave function doubles and a little bit more. Okay, so that's the normal, the default way it's implemented. But then you can also slow it down a little bit, so that the selection is made more precisely. So here you have this selection factor, so 0.5. So instead of so by default the selection factor is 1. So it's going to try to add 1 times the number of determinants that you have in the wave function. That's how it doubles. But with 0.5, if you have 100 determinants, you would try to add 50 and then add what is necessary for S squared. Okay, so this selection factor is a knob to accelerate or slow down the selection. So when you want to do QMC after, it's better to slow it down a little bit to really pick a small number of important determinants. And once you have reached this point, you will see that the extrapolation, the extrapolated excitation energy is consistent with what you expect, around 4 eV. And then we will export the wave functions for CHAMP, and then you will be able to optimize the ground and excited states to continue the calculation with the QMC. So I let you move on from here. So as I say, it's possible that we get different results because I run on my laptop with only 4 cores and you run with much more. Okay, so but the idea is really to have here a wave function that corresponds to the state you want with the important determinants inside, because this is what you're going to give to the QMC calculation. So so now if we look at the wave function with QP edit here, so we can go to the bottom of the file and search backwards for an equal sign. So this brings us to the the determinants. So what we see here is that so this will be the CI coefficient of state 1 and this of state 2 for this determinant. So you see that here the Hartree-Fock determinant has a large coefficient in the ground state, but has a 0 coefficient in the excited state. And then you see here that this singly excited determinant has his brother. I would say it's the same one with the so you have here the excitation on the beta part, and here you have the excitation on the alpha part, and they both have the same CI coefficient in the excited state. So the excited state is really the combination of this one plus this one with the same coefficient, and this has a 0 coefficient on the ground state. So you really see here that the excited state is the singly excited state, the homo-lumo singly excited state here, and you see that there are different symmetries, because when you have a coefficient on the excited state, it's 0 on the ground state, and when it's non-zero on the ground state, it's 0 on the excited state. Okay. So there it is. And okay, so now you have your wave functions like this. You can now export the wave functions for making the calculation with CHAMP. So now in the easy file directory, you have information for the 2 states. And so what we will want to do is really export we will want to export the data for 2, we will want to create 2 TXIO files, one for each state. Okay, so to do that, the simplest way is to copy the directory into a ground state and excited state, and then select which states you want to keep in each directory. So first, you select the ground state and you say qp edit -- state equal to 1. Then it will only keep state 1 in the directory. And so then you do the same for the excited state, and you keep only state 2. So let me show you what's going to happen. So if I do qp edit right now with this, sorry, here you have always 2 coefficients, one for the ground and one for the excited state. And if I copy the directory COH2 into COH2ES, qp set file COH2ES, and qp edit state equal to 2. It has extracted state 2, and now if I qp edit, you see here I have only one set of coefficients, and they correspond to the coefficient of state 2. Okay, so well, we also have many zero coefficients here. So now we will try to get rid of all those zero coefficients that are here. And so for that, we will call the truncate wave function program of quantum package. So let me show this to you. If you run truncate WF here, it gives you a histograms of the weights of the configurations. And basically you see that there are many configurations with weights lower than 10 to the minus 10. Okay, so here you can say I want to truncate to remove everything which is below 10 to the minus 10, and now it has so at the beginning we had how many determinants? 3,000 determinants, and now we have kept only 2,000. And if I QP edit again, here I see that I don't have these zeros anymore. Okay. And now all these small weights have been removed. We can export the wave function for CHAMP in a TREX IO file. And so you need to do this for the ground state and for the excited state. And then you will have reached a point here where you can really start to do the QMC wave function optimizations. So maybe what we can do, we can try to all reach the point here where we reach the end of section 3, and maybe do the QMC wave function optimizations tomorrow.